between 500 kilohertz and 1.5 megahertz. And the system was built using a white LED, and the output was verified with a pre-built fiber optic receiver to be exactly the output that we want. Another major problem resolved in this project is that of recovering the clock signal from the received optical signal. The problem was identified as the main difficulty in achieving higher speeds by the team that designed the free space optical transmitter receiver pair last year. The solution is a HD6409 Manchester encoder and decoder integrated circuit, which synchronously communicates with the rest of the circuit. It will work by encoding the data to be transmitted as Manchester code, which is sent to the LED driver. The decoder side then recovers the clock signal, which is embedded within the Manchester encoding. However, this solution requires many synchronous interfaces, a total of 6. 5 for optical transmission and reception, and 1 for the SPI, which interfaces with serial with the Ethernet module. Since it's hard to find a microcontroller with so many synchronous interfaces, an FPGA may be a better solution. On this slide, I summarize what has been done and what remains to be done. As mentioned before, the LED driver portion and the encoder, decoder portions are almost complete. What remains is to integrate these modules with the rest of the system. A suitable implementation for the Ethernet interface, the ENC28860, which provides a SPI interface for the Ethernet connection, has been selected. And what remains is to find an appropriate RJ45 Ethernet jack and to interface the device with the chosen microcontroller or FPGA. The photodiode receiver is half done. The preamplification and first filtering stage have been designed. What remains there is to select from a few candidates for the design of the second stage of amplifier and filters. However, no suitable microcontroller unit or FPGA has been found yet. And the power supply and optics for the receiver have also yet to be found. I will continue working on this and plan to have a finished system built by the end of the summer. I'd like to thank Professor Little for his support and Professor Hornstein for his advice on designing the LED driver. At this time, I will take any questions and comments. Thank you.
Questions?
When you established the link, was it a free space link? Or you said you used the fiber optic receiver, but did you just put it right up against the LEDs?
Yes, it's a good show. So the blue block here is the fiber optic receiver I used since the receiver isn't complete yet. And it was just a fiber optic cable that I held up to this light LED.
Okay.
And the oscilloscope output is this, where the top signal is that received by the fiber optic receiver, and the bottom signal is the one generated by the function generator.
Any other questions? Based on your, you did some work on simulation plus testing. What do you perceive is what the speed you think you can achieve? You talked about greater than one megabit per second. I was wondering if your simulations indicate what might be a limit that your design could achieve.
Well, the simulation As I mentioned, it can work from 500 kilohertz to 1.5 megahertz, which will mean that it can work at 1 megahertz quite comfortably. And with 1 megahertz in magnetic encoding, it can transmit 1 megabit per second. Add in the 2 other channels, and you can get 3 megabits per second. And then throw in possibly some error correction, and we'll get around 2 to 3 megabits per second.
Following up on that, did you experimentally increase the frequency or play with the apparatus to see where it started to fail, not communicate?
I did incrementally increase the frequency, but I wasn't able to determine what portion.
How high did you get?
1.5 megahertz. At that point, the quality of the signal received by the receiver depended mostly on the placement of the receiver in comparison to the LED. If the receiver was placed in one place, then the peaks, then the high states of the received signal would be very short. And then placed in another place, the high states would dominate most of the time, and the low states would be very short.
So with your scope trace that you just showed,
This is at
yeah.
1 megahertz.
So where would the short periods be in terms of the signal at the top?
So the tops would sort of blend together in certain places, and the tops would be extremely short, and I'm not sure if they can be detected if the receiver was placed in a different place. But at 1 megahertz, the receiver was quite comfortable with the transmitter. Yes.
What kind of error correction have you considered to do?
I haven't implemented any error correction code yet.
Have you thought about any?
I was thinking of throwing in some resolvement,
Why?
just because it doesn't consume that much bandwidth, and it can still be used to cover part of the damage signal.
Can you comment on the efficiency of the power circuit? How much power goes to the LED and how much power
A little over half of the power goes to the LED, the rest is burned on the circuit. This is because the voltage across the LED, the voltage that's needed across the LED to drive it at 350 milliamps varies a lot, and I needed to have that the available voltage to adjust in case I needed to. So the power supply voltage is fixed at 5 volts, and the LED voltage can be anywhere from 2 to 3.75 volts. So the varying voltage could easily be wasted on trying to get through the NMOS transistor, which can be set to really high resistance.
In your work, where do you see being the part of the technology that needs to be changed to get faster speeds? Like where in your system would need to be optimized? Like the LEDs, the coding, what would need to be done in the future to get faster speeds?
I think that while the LED driver works, it can be improved for faster speeds, and that's probably the main point.
Faster switching LEDs is something that might help.
If I were to use white LEDs, faster switching LEDs would probably help, but because of the long decay time of the fluorescent material, but color LEDs don't have that problem, so they can get through pretty fast.